To engineer electric vehicles and automated robotics, we have to start by designing materials at the microscopic level. This diagram shows the stark contrast in atomic anatomy. The tightly packed, positively charged nucleus, sitting at the center, holds almost all the mass. Meanwhile, the vast, mostly empty electron cloud buzzing around it makes up the atom's volume and governs how it bonds. The periodic table organizes all these elements for us. The vertical columns tell us the number of outer valence electrons, which drive chemical reactions. The horizontal rows show us how many energy shells surround that specific nucleus. Knowing how to read this map and understanding basic atomic anatomy is the absolute baseline requirement for predicting how any material will bend, stretch, or break under severe mechanical stress. This diagram shows the 2n² rule in the bottom left. This mathematical formula dictates the strict maximum electron capacity for any given energy shell. This chart displays the electromagnetic spectrum. It shows differing wavelengths and energy levels, from gentle radio waves to supercharged gamma rays. When these electromagnetic waves interact with an atom, they transfer energy, forcing electrons to jump between those specific energy levels. As we look at multi-electron atoms, the structure gets complicated. Because all electrons carry a negative charge, they naturally repel each other. This mutual repulsion warps the shapes of their orbits and significantly shifts their energy states. This chart outlines the diagonal filling rule. Because of that structural repulsion, electrons bypass sequential rows and always seek the lowest available energy states first, following the specific diagonal progression through the S, P, D, and F sublevels. This graphic shows the incomplete electron configuration for calcium, atomic number 20. Applying the diagonal rule, what orbital fills after the 3p6 state? The map skips the 3d shell entirely. The next two electrons populate the 4s orbital, completing the 4s2 configuration. Predicting these precise, non-intuitive orbital configurations is the necessary first step to predicting how complex materials will behave and interact at the chemical level. This breakdown of a robotic arm shows exactly how these atomic configurations enable advanced mechatronic systems. Look at the smart materials callout. By leveraging molecular-level polarization, materials like dielectric elastomers can physically flex and respond, functioning exactly like artificial muscles for soft actuation. This graphic details wide bandgap semiconductors in the upper right. By structuring atoms into precise lattices, materials like gallium nitride and silicon carbide can handle massive heat and voltage, enabling highly efficient power conversion for electric vehicles. This table highlights failure analysis. Identifying atomic-level crystal defects, like dislocations and grain boundaries, is how engineers predict fatigue and prevent cracks in microscopic MEMS actuators. A material's ultimate mechanical failure or success in a high-stakes system is entirely predetermined by these invisible atomic-level interactions. We quantify this structural durability using lattice energy. It acts as the invisible superglue holding crystal structures together, dictated by the exact equilibrium point where attractive forces perfectly balance against repulsive boundaries. This chart plots the correlation between lattice energy and melting point. High lattice energy indicates that atoms are tightly packed and locked, requiring immense amounts of thermal energy to break the electrostatic attractions. Notice the data point for barium oxide. Its high lattice energy pushes its melting point to 1923 degrees Celsius. Calculating this exact energy is how we select the heat-resistant ceramics required for extreme aerospace environments. This matrix maps dominant atomic bonds directly to their real-world mechatronic applications, from covalent bonds in graphene force sensors to metallic bonds in shape memory surgical tools. Mastering these microscopic atomic blueprints elevates you from building basic components to engineering the highly reliable, intelligent systems of tomorrow.